All right, so last time we finished off with looking at an example of finding an angle between two vectors. Okay, and I think we did this problem. Okay, so we had done example 3. So one thing we can do is, once we know the angle, we can determine if two vectors are parallel or perpendicular. Okay, kind of a very simple application of finding the angle. We don't really use the word perpendicular too much when we talk about vectors. They use this word orthogonal. But it means exactly the same thing as perpendicular. Okay, so on the test, if you have a problem and it says, which of the following vectors is orthogonal? And they give you different pairs to look at. They're just asking which vectors are perpendicular. Okay, so if two vectors are perpendicular or orthogonal, that's the symbol we use for perpendicular, what do you think that would mean the angle is between them? Josh? Yeah, it's 90 degrees. Okay, and there's actually a shortcut to figuring out if two vectors are perpendicular based on the fact that they would be 90 degrees. Okay, so let's take a look and see if we can figure out a shortcut for this. Okay. What's the formula for finding the angle between two vectors? Cosine of theta. Can you be more specific?
U dot v.
Yep.
Yeah,
U dot v.
and then the magnitude of u times the
Magnitude of u. Magnitude v. So, if they're going to come out perpendicular, you're going to have something like this. The angle would have to be 90. And then you would have the dot product, you'd have to figure that out, over the product of the magnitudes. Well, let's just figure out what the left-hand side would come out to. Okay, because we can figure that out. If they're perpendicular, what's the cosine of 90? 0. So if two vectors are perpendicular, when you do all the work out on the right-hand side, that fraction has to come out to 0. So what does that tell you? Yeah? Yeah, that the dot product would be 0. Okay, it doesn't matter what's in the bottom. The only way a fraction can ever come out to 0 is if the numerator comes out to 0, and the numerator is the dot product. So that's the shortcut for figuring out if two vectors are perpendicular. The dot product has to come out to 0. There's no point in going any further and checking the magnitudes. That doesn't matter. Okay, so we've got two vectors, 2i plus j, I plus 2j, and they want us to figure out if those vectors are perpendicular. Okay, so perpendicular, that's the easier case. Parallel, we got to do a little more work. It's more like a normal problem. But this one, just find the dot product. Okay, so what would be the dot product of v and w here? Yep, 2 times 1. And what is the next one?
plus
Yeah, plus
2.
1 times 2. So what's the dot product? 4. So what's the answer to the question? Are these perpendicular? No. You're going to get 4 divided by something. But 4 divided by anything is never going to come out to 0. Any questions on that? What could you change here to make these vectors perpendicular? Changing the smallest amount of stuff you could. Just like one thing. Yeah?
Instead of I plus 2j, I minus 2j.
Yeah, you could do I minus 2j. In fact, you could make any one of these a negative. Okay? If any one of those 4 numbers is a negative, just one of them, you could make the dot product 0. Okay, questions on that? All right, so that's perpendicular. And the next thing is parallel. So if orthogonal means the angle's 90, any guess what the angle would be if the vectors are parallel?
Parallel pipe, whatever you said. Wasn't that word before?
Oh, that's a geometry term.
Oh.
Yeah, that's a parallel pipe that doesn't have to do with
Oh,
vectors.
all right.
Yeah.
Never mind.
So I'm looking for a number.
Oh.
What would be the angle between two vectors that are parallel? Well, a vector by itself doesn't have an angle, so you can't really say the vectors would be. Like, yeah, it doesn't make sense. Yeah. How much? Yeah, that's one possibility.
0.
Basically, if you had vectors like this, the angle between them is 180, and they are parallel, because they would never cross, right? They would never touch. And what's another angle you could have? Yeah? 0, yeah. So 0, you could think of like that. Okay, they're pointing in the same direction. So same direction or opposite direction, the vectors are parallel. So let's see if we can come up with a shortcut for that one. We can come up with a little bit of a shortcut, but it's not going to be as quick and simple as just finding the dot product. All right, so let's start with 0. Okay, I'm going to do the same thing I just did up above. Cosine of 0. If they're parallel, what would be the cosine of 0? 1. So if the vectors are parallel, one thing that could happen is you get an angle of 0. The cosine of 0 is 1. So what does this tell you? If this fraction comes out to 1. Yeah, that would tell you that these are the same. So in order to compare if two things are the same, do you have to know both of them?
Mm-hmm.
Yeah. So you have to figure out the top and you have to figure out the bottom. You wouldn't have to go through the inverse cosine though. So if the top comes out to 10 and the bottom comes out to 10, they're parallel. But you still have to find the top and the bottom. Okay, and let's look at this case. Cosine 180. That's the case where the vectors point in opposite directions. What's the cosine of 180? How much? Yeah, -1. So kind of like the last one. But what does this tell you about that fraction? If it comes out to -1. It's not what we did last time. It's not that they're the same. Yeah, what do we call those? They're opposites. Okay, so basically if it comes out the same or the top and bottom come out to be opposites, you're parallel. Okay, so but there still is that one extra step. You got to find the magnitudes in the bottom. Okay.
Do you have this in writing?
In writing? Like,
It's just, I didn't know, like, because last time you showed us and had it.
I got an example I'm going to do, but that's all I got. All right, so I want to determine if those vectors are parallel. Okay, so we have to find everything: the dot product, length of V, length of W. Okay, so what do we got to multiply to get the dot product? First two things. 4 times 20. And -5 times -25. So that's going to give me 80 plus 125, 205. So now I already know what I'm hoping the product of the magnitudes is going to come out to, if they're parallel. What would magnitude V times magnitude W have to be? It would have to come out to 205. All right, so let's find the magnitude of V. What's 4 squared plus negative 5 squared? Yeah, so 16 plus 25 gives you 41. And now 20 squared plus 25 squared. Okay, what's 20 squared? So 400. And what's 25 squared? Okay, so 1,025. Okay, so I don't even need to plug in the whole formula. Just find the magnitude of V times the magnitude of W. That's the denominator. If it comes out to 205, they're parallel. If it doesn't, well, I already know they're not perpendicular, so they'd be neither. Okay? How do I already know they're not perpendicular? Yeah, the dot product is not 0. Okay, so let's find the square root of, and if you wanted, you could really just type it in like this, 41 times 1,025. That's the same thing as typing in each square root separately. And you get 205. Okay, so so we know when we multiply those, we get 205. And what would be the answer to the question? Determine if they're parallel. Yes. These vectors are parallel. Okay, another way to look at it, if you think of it in terms of a line, it's almost like asking if the point, think of both of these vectors starting from the origin. If you found the slope of the line that went through the point 0, 0, and 4, negative 5, and then you found the slope of the line that went through 0, 0, and then 20, comma, negative 25. If you found the slopes of each one of those lines I just explained, they would come out the same. If you thought of V and W as coordinates and not vectors, both going through the origin. So any questions on that? All right. So as far as the perpendicular parallel, that's it. That's the only other thing that was new. Okay, this it's going to be a velocity vector, and I think from yesterday you're already going to know how to do it. So what we're going to basically look at is a plane that's flying and the wind is going to blow it. I want to know how the wind is going to affect the speed of the plane and how it's going to affect the direction. So first of all, the problem is going to talk about two different types of speed. One is going to be airspeed. And the other speed it's going to talk about is ground speed, like somebody observing the plane from the ground. Okay? So kind of like if somebody had a radar gun and could point it at the plane and get the speed of it, what would be the speed that they would observe from the ground? Can anybody explain the difference between those two speeds, airspeed and ground speed? Because they're very rarely the same for an airplane. Almost never. Yeah?
Is ground speed like the speed of the plane taking into account the wind resistance or?
Okay, yeah, it's basically taking into account the wind. So the idea is like, if you were going down the highway and let's say there was no wind, okay, the wind was perfectly calm, and the speedometer says 50, and you put your hand out the window, the air is hitting your hand at what speed? 50. Right? It's 50. Now, if you change it, and let's say the wind is blowing directly at you at 20 miles an hour. Okay? The wind is blowing at the front of the car at 20 miles per hour, and the speedometer says 50. And you put your hand out the window. So now the wind is hitting your hand at 70. So even though the speed of the car is still 50, because that's what the speedometer says, the wind speed is 70, or airspeed. Okay. So any question on the difference between airspeed and ground speed? Okay. So really, the only important things you need to know is that the plane airspeed is 500 miles an hour south. Jet stream is 80 miles per hour northeast. Find the speed and direction of the plane. Okay, we'll definitely do the speed. I'm not sure, well, maybe we'll do the direction. So the direction of the plane has to do with an angle. Right? And to find an angle between two vectors, that's where the dot product would come in. So everything in this problem, if I took out direction, you could have done yesterday. But if I want to know the direction, that involves the dot product. All right, so what do you think the first thing we should do with all of this is? Set up what? Yeah, we'll set up a diagram. Anytime we have a word problem, it just kind of helps to visualize what's going on. Okay, so I'm going to draw all this out on here. So the first thing is I have a plane flying 500 miles per hour south. Okay? Just to be clear, what direction is south on here? Down. Okay, so this would be south, that's west, north, and east. All right, so I'm going to put in the plane flying 500 miles an hour south. It's not to scale. Okay, but that represents the velocity vector for the plane. So I'm going to call that V sub p. Okay, and then I have, let's see, the jet stream is 80 miles per hour northeast. Okay, and northeast means exactly between north and east. Okay, and I'm going to draw that arrow a little shorter because it's 80 miles an hour.
Is it VP or UP?
V sub p, velocity vector for the plane. And I need a little more space. Let's call this one the velocity vector for the wind. Okay, and they want us to find the actual speed and direction. Well, if I kind of want to figure out what's going to happen to the plane, I could just take this vector and move it. I don't want to right-click on it, so we'll just like to move it there. And what's going to happen to the plane with the jet stream if the pilot doesn't adjust anything is that the plane's going to go in this direction. So what are the two things that are going to happen to the plane if the pilot doesn't adjust for the wind?
It's not going to go to the right place.
Okay, so why? What's going to happen?
It's going to end up going southeast.
Yeah, his direction is going to change. And what else? And the speed is going to change. Okay. Sometimes the wind could speed the plane up. Sometimes it might slow it down. What is it doing in this case?
Slow it down.
Yeah. So we'll call that vector in black the actual velocity vector of the plane. And basically the actual velocity vector takes into account the plane plus the wind. Okay, that's how you get the actual velocity vector. Take the plane and the wind and add them up. Okay, so what we have to do is find V sub p and V sub w. We have to figure those out in terms of I and j. So using our cosine and sine, just turn that into a velocity vector. Let's start with V sub p. Okay, to write a velocity vector, what's the first thing you need to know? Think about from yesterday. What's the first thing you write down when you put down a velocity vector? the magnitude. And in this case, the magnitude of a velocity vector is really the speed. So we're starting with the velocity vector for the plane. What's the speed of the plane? 500 miles per hour. And now in addition to the speed, I also need the angle. So the way we do our angle is not the way a compass does it. We do it the way we've always done it. So what angle would south be? On the way we do it, it's 270. That's not the way it is on a compass. Okay, but it's 270. So cosine 270 plus I sine 270. Okay. So do that out, and we'll have the velocity vector for the plane. Right, so I'll type in,
Oh, yeah. Yeah, we're not doing complex. Isn't it I and J and not cosine 270 plus I?
oh, yeah, thank you. I was thinking, it's very similar to complex numbers, but it's a little different.
Yeah.
Okay, so now do that out and see what we got. Cosine of 270 is 0. So that means we're not going to have any horizontal component. That means basically all the velocity is going in one direction. Okay? And that should make sense here, because look at the red line. It's on an axis. If you draw a vector on an axis, one of the components is 0. In this case, the left and right component is 0. Okay? And now I need the sine of 270. Times 500 is going to give me how much? Negative 500. Okay, so really, you can just write negative 500j. And why does the negative make sense here? Yeah, because it's going south. Okay, anytime you have a direction that's west or south, you should get negative numbers. Okay. Right, so there's our velocity vector for the plane. And now we'll do it for the wind. What's the speed of the wind? 80. And what's the angle of the wind? And the angle is always relative to east. Yeah, the angle is 45 degrees because the wind is blowing exactly between north and east. So if it's blowing exactly north and east, what does that mean about the horizontal component and the vertical component of the wind? It's the same. Okay? It's exactly the same. So we've got 80 cosine 45 plus sine 45. And once I figure out the first component, the second one is going to be the same. The cosine of 45 and the sine of 45 are both 0.707. They're the same number. Okay, so let's just do the first one. 80 cosine 45 is 56.57. Okay, so the jet stream is blowing the plane 56.57 miles per hour towards the east and 56.57 miles per hour north. Actually, I don't really need a parenthesis anymore. So that's quite a bit. So that means for every hour that the plane is traveling, if the pilot doesn't adjust, he's going to be 56 miles, almost 57 miles off course. So after 7 or 8 hours of flying, it could be hundreds of miles from where he's supposed to be. All right. So we've got the velocity vector for the plane and the wind. And now what do I do with the two of them to find the actual direction of the plane? Add them up. Okay, so to find the actual direction, take the plane, add it to the wind, and that's what we got. Okay, so let's look at the I component. Is there any I component for the plane? No. So then all I have to do is take the I component for the wind. It's plus 0. Okay, nothing to combine it with. So 56.57 I. And then, is there a J component for the plane and for the wind. Yeah, so this time I got to take negative 500 plus 56.57. Negative 500 plus 56.57 gives me negative 443.43. So this tells us that the pilot really, if he's trying to fly south, he's only going south at 443 miles an hour. He's not going south at 500 because of the wind. So there's our vector. Now we can find anything they want us to find. We could find, let's do the speed of the plane. Okay, the ground speed. So like if somebody was on the ground and had a radar gun, this is how fast the plane would be flying. So the speed is basically the what of this vector? Yeah, it's the magnitude. Okay, and I'm just going to type it, I'm going to type it all in at once. It's going to be the square root of square root. And what would I type in? 6.57 squared. Yeah, you could type the negative, or you can leave the negative off, because when you square it, the negative is going to cancel out anyway. So I'm just going to do 443.43, square it, and I get a ground speed of about 447 miles per hour. Seems a little off, but we typed everything in right. You don't need parentheses around that because there's no order of operations. The exponent will be fine. Okay. So there's your ground speed. All right, now the direction of the plane, you could describe it a couple different ways. You could either find this angle or that angle. And really, once you find one of them, you have them both. It doesn't matter which one you find, but then once you find it, there's a certain way you have to phrase the answer. We're either going to say the answer, the plane is flying a certain number of degrees south of east, or it's flying a certain number of degrees east of south. Okay, so depending on which angle we find, we could say it different ways. So which angle do you want to find? The angle with east or the angle with south? Okay, the angle with south. So what we're doing now is we're finding the angle between the red vector, or between v sub p and v sub a. So to find that angle, what do we have to do? What are the three things I need? I need the dot product. So let's find that first. We already have one thing we're going to need. Okay, the dot product between v sub p and v sub a. V sub p is a good one to use because the number, the I component is 0. So we don't have to worry about that part. Okay, so let's see if I can get both of these at the same time. Okay, so we're using this and that. Okay, so what do you get when you multiply the I component in v sub p and the I component in v sub a? 0. Okay, so that's 0 plus, now multiply the j component in v sub p and the j component in v sub a. So it's going to be negative 500 times negative 443, and that's going to cancel and become a positive. So 500 times 443.43 is a big number, 221,715. Okay, so I need the dot product. What else do I need? The magnitude of v sub. Yep, I have that. So I've got that, I've got that, and I need one more magnitude. V sub p. which again, this is going to be a pretty easy vector to find the magnitude of. What's the length of V sub p? It's just 500. If you want to use the Pythagorean theorem, it would be 0 squared plus negative 500 squared, and then take the square root. So it would just be 500. Okay, so those are the three things you need to find the angle. Now just fill them into our formula. Inverse cosine. Yep, the dot product. I was just looking at it for a second. The dot product, which is 221, 715, over the product of the magnitudes. So 447.02 times 500. Okay, the reason I was looking at it for a second is because the bottom has to come out bigger than the top. If it doesn't, you're going to get a domain error, but I'm hoping 447 times 500 is bigger than the top. Great, so let's type it in and see what we get. So let's clear that. So inverse cosine of 221, 715. 715. Okay, divided by, and you probably don't need parentheses here, but yeah, actually I don't think you need them. Order of operation should be fine. 0.02 times 500. It doesn't really matter since that's all multiplication and division. If it does 221 divided by 447 first. Now, you know what? I don't trust the calculator. I'm going to put parentheses in. If you have a calculator and try it without, let me know if you get the same answer. Okay, but now it'll do the denominator first, and then it'll do the inverse cosine. Yeah?
You didn't separate 221 and 715, so that's 20,000.
That's a comma. Yeah, the dot product was 221,715. Yeah. Okay, so the angle is 7.2, we'll say 7.3 degrees, which seems reasonable because that's a very small angle. What was it? 7.3. Okay, so it's 7.3 degrees, and the way you would word it, it's 7.3 degrees to the east of south. So you write east of south. Or the other way you could say it, if you did 90 minus 7.3, that's 82.7. You could also say 82.7 degrees south of east. Is there any question on the wording for how you phrase that answer? That east of south. So that's how many degrees the plane is going to be blown off course. Yeah, so any questions on that one? Okay, so as far as word problems, that's most of the word problems, I think all of them that we're going to see this week. All right, so last thing we'll look at and probably finish tomorrow is 3D vectors. Okay, so what you're looking at there, that's basically x, y, z axis. Everything we've done up until right now has been in this area. Okay? Think of that plane as the ground. Okay? The z-axis is coming up off of it. Okay? So if the table was the xy plane, the z-axis is coming straight up from the table. Okay? And one way you can kind of figure out which way things are pointing, this is called a right-handed coordinate system. I think that's in your packet. And basically, if you let your index finger point in the direction of the x-axis, your middle finger points in the direction of the y-axis, and your thumb would point in the direction of the z-axis. Okay? If you do it with your left hand and line up your index finger and your middle finger, what happens is your thumbs point in opposite directions. So the z-axis is pointing the wrong way. That's what happens. So it's a right-handed coordinate system.
The one we learned in shop, this is easy. The one we learned in shop.
Oh, you do it a little differently? Yeah, that's how the book, if you look on page, I think it's 354. It says, your index finger points in the direction of the positive X, middle finger positive Y, thumb positive Z. Yeah, there might be different ways to do it.
Yeah.
Maybe that's how we do it. We're not going to do much sketching in 3D because the sketches, they're kind of hard to do. So we're going to focus more on calculations without sketching. Okay, so basically what I'm going to do is every formula we learned in 2D, I'm going to put it up again to remind you, and then I'm going to write the 3D version. So you really don't need to write the 2D version and then the 3D version every time, because you already have the 2D version. Okay, so this is the distance formula in 2D. Okay, and you would be given two coordinates, x1, y1, x2, y2. Well, in 3D, okay, the difference is you're given two coordinates, but there's an x, a y, and now there's a z component. Also, the other thing, when you're working in a 3D coordinate system, it's not called quadrants anymore. Okay, quadrants is when you have 4 regions. In 3D, that's not what you have. Does anybody know how many regions there are in 3D? No, not 6.
7.
7.
I like the number 7. Really, it's true.
Well, think about it like this. Pretend the z-axis comes out of the board. So
That's fine.
one option you could go is you could go right, you could go up and come out of the board. That's one region. You could go right, you could go down, and you could come out of the board again. That's the second one. You could go left, down, and come forward. You could go left, up, and come forward.
Could you go down too?
Yep, I said the downs. So you got, those are the 4 places you could go. But what else could you do instead of coming forward? You go
That's
back.
what I meant when I said down.
Yeah. So you could go right, up, and behind the board. Right, down, and behind the board. Left, down, and behind the board. Left, up, and behind the board. So how many regions is that? Nope. 8. 8 different regions. So, does anybody know what we call 8 regions? Well, we don't call them quad. Octants. Quadrants, octants. So, in 3D, you have what are called octants, and there's 8 of them. So every time you add a dimension, it doubles the number of regions. Think about a number line, 2D, right? Put 0 in the middle. You've got left and right, 2 places. That's 1D, just a line. 2D, now you've got 4 regions. It doubles. 3D, 8 regions. And then 16 regions, and so on. So the distance formula in 3D, it's exactly the same as 2D, except you add the z component on the end. Pretty much every formula we do, that's all you have to do to extend it to 3D. That's why I said if you're going to make a reference sheet for the test, just put the 3D version, and then if you're doing a 2D problem, you just cross out the 3D part. You don't need it. Okay, so we'll start off by finding the distance between those 2 points. If they don't label which one is which, always assume the x1, y1, and z1 goes with the first point, and the x2, y2, z2 is the second point. It doesn't really matter as long as you're consistent when you set it up. Just do it the same way for each parenthesis. Okay, so what would be the first calculation? All right, so we've got 4 minus 1, or minus negative 1, squared. Yep. Negative 2 minus 3. 5 minus 2. A couple other things we need there. 1 and the square root of it. So we're going to get, let's just do each one. 4 plus 1 squared. 25. Negative 2 minus 3 squared. It's also 25. And 5 minus 2 is 3 squared is 9. So what's the distance? Square root of 59. Okay, all the regular rules that we use with square roots still apply. If you can reduce it, we do. Okay. And that's it, yeah. So any question on finding distance in 3D? Okay, this is not a vector-related thing, but everything else we do is going to be vectors. But since we're talking about 3D, it's kind of good to start with the most basic thing you can do in 3D. Even more basic than working with vectors is just working with 2 points and find the distance. All right, so in 2D, okay, the way we represent vectors is we have an x-axis component represented by the first term. Then we have the y-axis component, and that's the second term. So now we're going to have an x-axis, a y-axis, and a z-axis. So A is the x-axis component, B is the y-axis, C is going to be the z-axis, but we also need to put a unit vector with it so that you know it's the z-axis. So I is the unit vector for the x, J is the unit vector for the y, and K will be the unit vector for the z-axis. Okay, if you wanted to write it in the algebraic notation, that's what we call the angle brackets, it would just be A comma B comma C. So just like in 2D, you should be able to work with either notation. So any questions on how to write a vector in 3D? Okay, so the A, the B, and the C, those are the components. I'm not going to say the horizontal and vertical components anymore, because when you're working in 3D, that can be a little confusing. I'll say the x-axis component, y-axis, or z-axis. Okay, this you already have in your notes from earlier in the week, and it's exactly the same in 3D. If your vector starts at the origin, it's a position vector. We said that in 2D as well. Okay, so to find a position vector in 2D, that's how you do it. And when we did it, we went through a whole sketch and we looked at it. So we're not going to go through it again. And it's important you do subtract in the right order when you find a position vector. It's terminal minus initial. For the x components, comma, and then the y components. What would happen if you switched the order you subtracted? What if you did x1 minus x2 and y1 minus y2? What would that ultimately do to the vector that you get for an answer? Well, subtracting them in the wrong order would change something about your answer, but it would also leave something else the same. Yeah?
It changed the direction of the vector.
Yeah, you'd get a vector with the wrong direction, but it would be the right magnitude. All right, so just do it in that order so we don't get the wrong direction. Okay, so now in 3D, we're going to have an initial point and a terminal point. The only difference is it's going to be a 3-dimensional coordinate. And what do you think I'm going to have to do to my position vector formula in 2D.
Just add Z2 minus Z1.
Yeah, just put on Z2 minus Z1 on the formula. So now if you copy that formula down and you're doing a 2D problem, just pretend Z2 and Z1 are both 0. That's basically what we've been doing all week. You could consider everything we did already was 3D. It's just the 3D component was always 0 minus 0. So we don't write it. But now it might not be 0, so we have to write it. So finding a position vector is kind of like doing the distance formula. There's some subtraction, but you're not squaring things, and you don't take the square root. So it's actually a little bit less in terms of a calculation. Okay, so let's do this one, and let's write it with the angle brackets, and then we can do it with the ijk. Okay, so what would my x component be? 5, right? 4 minus -1. My y component, and my z, -1. If I wanted to write it with ijk, how would I do it that way? You could do plus a negative, but I would just do a minus. That's a little easier. So minus, you could put 1k, or you can just put k. There's always understood to be a 1 there if you don't put anything, or in this case, a -1. Okay, so either way. Okay. Questions on finding a position vector in 3D? Right? So the next thing we looked at, again, we're skipping over all the sketches. You could still do things in 3D, just like we did in 2D. You could connect the end of one vector to the beginning of the next and draw the diagonal. It would just be a 3D sketch. But instead of the sketching in 3D, we're going to go right to our calculations. So if you want to add two vectors in 3D, it's really just like 2D. You add the x's, you add the y's, now you have to add the z's. And I also put subtraction in the same formula. I just wrote plus or minus. So if you want to subtract vectors, subtract all the components. Okay, and we'll do one of those. Okay, what's another operation that we did in 2D besides adding vectors and subtracting vectors? It was before we did dot product. We scaled them. And scaling works exactly the same way. What did we do when we wanted to scale a vector? Multiplied each component. Yeah, take each component of the vector and multiply it by the number. Okay, so in 2D, we did it to the x's, the y's, and now we have to do it to the z's. So it's like just distributing that number to each component. Okay, and the last similar kind of formula we had when we did it in 2D was to find the magnitude of a vector. Okay, what was the magnitude of a vector in 2D? What was the formula? The square root of? Well, yeah, the x squared, and then plus y squared. And for 2D, that's what you had. How are we going to make it 3D? We're going to add z squared. So this is basically the Pythagorean theorem in 3D. Not basically, it is. We've proved the Pythagorean theorem in 2D. I think we did it. And we could prove it in 3D as well. It's pretty straightforward. Any questions on those formulas? Okay, so we'll try, probably not one of each of them, but we'll at least do we'll do the adding, I'll skip over subtracting, and then we'll do a scalar, and then a magnitude. Okay, so let's do V plus W. Kayla, what would be my I component in V plus W? Yep, 5. I. Jeff, my J component?
Be -1.
Yeah, -1. So we could put the -1J, or you can just put -J. And my K component, how about Ayla? How much? 7? 3. Right, so we're just adding all those numbers together. Okay. Questions on that? If you wanted to do it with the angle brackets, what would your 3 numbers be? 5, -1, 3. With the angle bracket, you have to put the -1 because you got to put something. But with the IJK, you don't need to put the 1. Okay. How about the magnitude of V? I'm going to take the square root of what plus what plus what? Plus 4. 4 plus 9 plus 4. Just squaring each component. How much is that? Yeah. 17 is prime, so we can't reduce that. And the last one is, what is this called? It's a scalar product, and it's 3W. 9, -12, 15. All right, so we just write that down. 9, -12, 15. Okay, so any question on adding, subtracting, scaling, or finding the magnitude in 3D? Okay. So I said it's really a good review because it's really the same so far. Right, so next thing, or last thing I think we did in 2D was the dot product. Well, dot product and then finding the angle. So anybody have a guess how we're going to do the dot product, what the formula will be, based on what it is in 2D?
X1 times X2.
So x1 times x2.
Y1 times Y2.
Anything we're going to do before that?
Plus.
Plus.
Y1 plus C1 times C2.
Yeah, plus c1 times c2. So just like all the other formulas, it's just adding that third part onto the end with the z's. Okay, so let's find the dot product between those two vectors. And we'll find the angle between them eventually, but if we find the dot product first, then that'll also help us to do the angle in a little bit. Does everybody have the formula? V dot W. Would the dot product be commutative in 3D? Like if you switch all the x1 and x2, y1, y2, and z1 and z2 in the parentheses, just switch them? Yeah. Since regular multiplication is commutative and the dot product is based on regular multiplication,
You didn't change it, you just had
it's still commutative. Okay, so let's, we'll write it out. Okay, first two numbers I would multiply for my dot product. 2 and 5. -3 and 3. 6. And remember, if there's nothing in front of it, make sure you look at the sign to determine if it's a plus or a -1. Okay, so the first product is, next one, and the last one. So 10 minus 9 gives me 1, and 1 minus 6, negative 5. So just by knowing the dot product, we should already be able to tell something about the angle between these vectors based on 2D. What could we say? Can't say what the angle is, but we can definitely say what it isn't. These vectors are not perpendicular. Okay? The exact same rules that we learned for finding angle in 2D apply in 3D. Okay, so if we had two vectors in 3D and we want to find the angle, what was the formula in 2D?
Cosine the dot product over the
The careful, cosine of theta equals what you just said. The dot product over the product of the magnitudes. Well, it's exactly the same in 3D. The only difference is it's a 3D dot product, which we just did, over a 3D magnitude, which we just did on the other page, times another 3D magnitude. So the formula is exactly the same, it's just there's an extra step in calculating those three things. It's the same formula. So we'll find the angle between the two vectors we just looked at in example 4. That might be a good place after we do that to stop. Okay, so let me just make sure I copied them right. So I have 2, negative 3, 6. Yeah, and 5, 3, negative k. Yeah. Did everybody have the formula? It's the same formula. All right, so the dot product, we already have that. It was negative, what was the dot product? Negative 5. And now we need the length of u and the length of v. So length of u, what's going to be the first number? 4 plus 9 plus 36. And that's going to give me the square root of 49, which is 7. Okay, and now length of v, 25 and 1. Square root of 35. Okay, so now the three things I circled, just fill them into the formula. Or if you want to take the inverse cosine right away, we can just set it up that way. So get theta by itself. So inverse cosine, what goes on top? The dot product over. Now, can I multiply the 7 times the 35 under the root? No, because the 7's not under a root. If the 7 was, then I could just put 35 times 7 under the root. But make sure the 7 is outside the root. Okay, so inverse cosine of negative 5 over, and again, I would put parentheses. I kind of debated last time, but I think it's a good idea to type it in just like that. Okay, so we get an angle of 96.9 degrees. And that's a 3-dimensional angle between the two vectors in space. Okay, so any question on angle in 3D? Okay, so everything we did up to that point is basically a review of 2D. Okay, the cross product we'll look at tomorrow. That's not something we did in 2D because you can't. There's no such thing as a cross product in 2D. It's a 3D concept. So tomorrow we'll look at cross product. We'll learn a rule for how to take the cross product. Okay, there's many, many ways to do it. but without knowing a lot of other things, this is probably the easiest way to explain it. Because you don't need to know anything else to use this rule other than just the rule. We'll do an example of finding a cross product. We'll test if a cross product is commutative. Okay, do you get the same thing when you do it in a different order? I think I already mentioned about that. And then we'll do something with an angle, and I'm probably going to skip over this. This is a calculus application, finding the torque pulling on a lever. So if you take calculus next year, you'll probably do that kind of problem. But, yeah. All right, so for tonight, okay, on 363, we're not doing all of that. So the cross product part and the torque problem, we can definitely skip all of that. And then I think up to 51 you should be okay with that. And then from last night's homework, you already did parts A and B on page 352. So I want you to do, which ones was it, 7 to 11? I want you to do 7 to 11, part C. So now that, or if you didn't do part B, I know some people didn't, you have to do part B. But part C is just saying are the vectors parallel, perpendicular, or neither. If you already know the angle, that should be quick. Okay, so we'll finish 3D vectors tomorrow in class. The part of the test I had you start tomorrow wouldn't cover anything beyond what we did today. Okay, so cross product would not be on the test tomorrow, things like that. Yep, if you want to come in the morning to start the test, you can. Just remember it has to be done by Friday at 2:40 for the end of the term. And I'll be after school tomorrow as well.